Nice to meet you everyone. My name is Masashi Yamamoto, Fabtech Japan Corporation, Steel Bridge Fabrication. I'm in Osaka, Japan now. Today, I would like to talk to you about experimental study on the shrinkage behavior of steel concrete composite slab. In recent years, the number of rationalized bridges has increased from the viewpoint of rationalization and cost reduction in Japan. Steel concrete composite slabs are widely adopted from the viewpoint of rational structure members, and the workability improvement of steel bridges and their numbers continue to rapidly increase in Japan. A steel concrete composite slab is connected between the concrete and bottom steel plate by a shear connector. The thickness of the bottom steel plate controls the tensile force acting on the slab. The highly troubled slab structure with high fatigue durability allows longer spans between the main girders. This figure shows a detail of steel concrete composite slab. Fabtech Japan Corporation developed a rigid type of shear connector with steel pipe that passes through the long hole on the steel rib. The load carrying capacity and durability have been confirmed to be equal to or more than those of headed stud and per-pound rib, because the long hole in steel rib is filled with concrete. In addition, the photo shows the construction stats of steel concrete composite slab. The thickness of the bottom steel plate controls tensile force acting on the slab. The specified values applied for the drying shrinkage effect in design of the composite girder bridge based on the highway bridge specifications. These values are applied to reinforced concrete slab, pre-stressed concrete slab. The steel concrete composite slab is the effect of drying shrinkage is expected to be higher owing to the restraint of steel materials. The purpose of this study is to evaluate the effect of the drying shrinkage in the steel concrete composite slab. Numerical calculation focusing on drying shrinkage in steel concrete composite slabs and reinforced concrete slabs were conducted applying a slab model. The effect of the bottom steel plate on drying shrinkage was determined applying single slab specimens. An analysis model that considers concrete drying shrinkage is proposed based on numerical results. The numerical calculation focusing on the time-dependent behavior of drying shrinkage in steel concrete composite slabs and reinforced concrete slabs were conducted applying a slab model. Based on the analytical results, a stress-strain relationship for drying shrinkage of concrete is derived as follows. This figure shows the strain distribution and amount of shared cross-section force change over steel concrete composite slab. This figure shows the section of the reinforced concrete slab and steel concrete composite slab respectively. A comparison of the change of stress in a given cross-section of drying shrinkage must include the degree of restraint. The analysis models include specimen types 2 to 4 and the investigate conditions are listed in this table. The figure shows the relationship between the final drying shrinkage value and change of stress. Except for the lower edge of the steel concrete composite slab, a gradual change of 0.3 Nm per final drying shrinkage value at 200 micrometers is observed. Conversely, the change of stress on the lower edge of the drying shrinkage value at 200 micrometers, which confirms the strong effect of the final drying shrinkage value. The The results confirmed the importance of evaluating the final drying shrinkage value, which includes the influence of the bottom steel plate in steel concrete composite slabs. These tests were performed to determine the influence of the bottom steel plate on the drying shrinkage behavior. Specimens of type 1 to 4 were installed in the basement of the Osaka Institute of Technology to maintain constant temperature of humidity. Type 1 is plain concrete without reinforced bar. Type 2 is reinforced concrete slab. Type 3 is a steel concrete composite slab. Type 4 is a reinforced concrete slab with a bottom steel plate. The specimen shape was a 1 square meter plate with a thickness of 260 mm. Aluminum tape was attached to the side surface to ensure that the upper and lower surfaces remained dry. Teflon plate was laid on the support plate to reduce the influence of friction. The concrete mixture proportions and material properties are as shown. This figure shows the drying shrinkage strain at the center of the specimen, where compressive strain is negative and tensile strain is positive. The strain of both specimens includes and type 1 showed the highest strain value, 431 micrometer. The amount of strain decreased with increasing amount of steel contained within the concrete of type 2 or type 3, whereas the strains of type 3 and type 4 were essentially the same. These figures compare the drying shrinkage strain distribution of type 2, type 3, and type 4. Type 2 shows that the strain of the upper reinforcing bars and concrete are nearly the same in this analysis and test. Phi SH equals 4. Type 3 and type 4, the difference between the analysis and the test results clearly increase upon approaching the bottom steel plate. In particular, the bottom steel plate in the test shows tensile strain compared with compressive strain in this analysis. It's hard for water in the concrete to dissipate because the bottom surface is covered by the bottom steel plate. Thus, the drying shrinkage value on the bottom of the specimen is smaller than that on the top. This table shows the specifications of the analysis model. Also, the conventional model type A and proposed model type B are shown in figures. This figure converts the analytical and experimental results. Proposed models type B1 and type B2 show that the drying shrinkage value at the concrete bottom and reduced to 1/3 of the top values. The shrinkage strain of the upper reinforcing bar and concrete of the proposed model are nearly identical with the measured value. Finally, I will conclude my presentation. The drying shrinkage of the steel concrete composite slab was investigated numerical analysis and drying shrinkage tests. A comparative study was conducted to clarify the effect of the bottom steel plate, and the analysis model is proposed. The conclusions are summarized as follows. The numerical results indicate that steel concrete composite slabs are more affected by the restraint of drying shrinkage than reinforced concrete slabs, and that these results are a factor that controls crack generation. The stress on the lower edge of steel concrete composite slab is also strongly affected by the final drying shrinkage value. The drying shrinkage strain distribution of reinforced concrete slabs type 2 shows a nearly identical creep coefficient 4 in the analytical and measured results. The test of reinforced concrete slab with type 4 and without type 2, a bottom steel plate, demonstrates effect on the drying shrinkage behavior. The drying shrinkage strain distribution of steel concrete composite slab and reinforced concrete slab with a bottom steel plate shows that shrinkage is not uniform in the cross-section with the bottom steel plate. To clarify the effect on drying shrinkage of steel concrete composite slab, an analysis model is proposed and validated. The analytical results approach measured values when the concrete cross-section is divided into two, and concrete shrinkage tends to behave according to the steel material ratio. Thank you very much for your kind attention.